So I want to focus on one specific thing. I want to focus on error in machine learning because machine learning builds on the notion of error and it requires error. And then I'm going to talk a little bit about how we train our models, and then I'm going to talk about how we measure error and try to minimize that and what that means. So to start off with, I'm going to talk about coin flips because it's the first example in every probability book. And the notion is that if you have a fair coin, then there's a 50-50% chance of you, or there's a 50-50 chance of you guessing the right side will come up. And if you do it 100 times, it should average out to 50 of those times. If you do it if you flip a coin 100 times, and 100 different people do that, then it should average out to about 50% of those times it'll be heads or tails. But the important thing here is that it'll average out. So we're looking at a probability, and we're looking at, well, in any one trial of 100 coin flips, we might have one of the flips be, one of the sides be more prevalent. And if we imagine that any given person in here is able to guess 9 out of 10 coin flips correctly, we're probably going to say that they're really lucky. If they guess 99 out of 100 coin flips correctly, we're going to think that there's something else going on, that they know something that they shouldn't be knowing. And exactly the same with machine learning. If our models do too well, then we know that there probably is something that went wrong along the way. And particularly with problems like hate speech detection, where we know that it's notoriously complex, and it's a complex problem that we're trying to figure out. But let's try to imagine that we build a system, a machine learning system, to predict coin flips. Well, we're going to need to guide the system in what to look at, or at least for some systems. So we might tell it to look at the material composition, the weight, the size of the coin. But there's something missing here, and that is that people flip coins. So imagine that we have the people in that room, or in this room, all flip a coin 100 times. We might want to look at some information about the people who are flipping the coins. So we might look at the height of the person, how tall they are, how high they throw the coin, how strong their thumb is, the size of their arm movement, and so on. So we might look at a bunch of different physical attributes of that person, and maybe this will help us boost our performance to about 70% of the time we're right when trying to flip a coin. But even though we don't ask for information about gender, ability, age, and health, and so forth, our model will probably encode some of those aspects, and we'll probably capture some of that. And similarly, with issues like abuse detection and annotating for abuse, we very often capture biases that our annotators have, even though we give them guidelines. So this is another place where error comes into it, but it's not necessarily an error we control. And when it is an error we control, a lot more questions come out of it. One other thing that machine learning assumes is that we have a representative sample of people. In this room and in that room, there are no children. So if we train the model to predict the coin flip using these features of height and so on, if we then had any child try to flip a coin that was not as tall as any of us, their movements, all of these attributes would be different. So the model would try to approximate to the closest point that it knows, and it would probably get it wrong. Like, it would probably just say, well, you look sort of like the shortest person in the room, so we're just going to assume you're like that. This is not such a big issue for coin flips, but it might be a much bigger issue if you're looking at or what kind of hate speech and what kind of abuse you're annotating for, and say, well, we're then going to try to predict. Well, let's look at if it's hate speech in the forms of threats that we've annotated, and we then want to try to predict for cyberbullying. We're going to get a system that performs really poorly, even if the results might be good of it initially. So I've tried to talk a bit about, or come into the fact that language is a bit more complex than some things. We all produce language as a function of our identities. So the way that every single person in here says something will vary from one another. This also means that the cultures we're embedded in when we say something will be slightly unique to each other. And if we then look at hate speech, we're then saying, well, we're going to give you, the annotator, a document. We're not going to tell you anything about the document, but we will ask you to judge whether it's abusive or not, whether it is hate speech or not. So even though we give the annotators guidelines, we still end up with their understanding of what and their own cultural embeddings put into the annotations. So like a question ends up being, what do the models learn? And that really depends on the specific type of models. So I'm focusing on two different types, linear and nonlinear models. So linear models are well-known statistical models, like logistic regression. And what's interesting about those is that they require that we specify the features. So we specify what the model is supposed to look at. That requires something really simple, but it requires that we have an understanding, or at least an intuition, about the problem that we're attacking. And because we specify these features, because we tell it what to look at, it also becomes much easier to interpret, well, what contributed towards this prediction. So if we return to the coin flip, if we say, well, how much did the weight of the coin contribute to your prediction that it's going to be, the result is going to be heads, we can pretty directly audit that. For nonlinear models, that auditing is a lot harder because we might not, for some cases, and very often, we do not specify the features. We simply say, here is data and here are some labels, and now train yourself to find out what works. So we don't really necessarily know what it's looking at. We don't necessarily know what it's finding. There's a lot of work that goes into breaking the black box of neural networks and nonlinear methods, but it's still fairly early days in that, so there's still a lot more that we don't know. And further, because we don't need to specify what the model looks at, we don't actually need to have an understanding of the problem that we're attacking, which I think is pretty dangerous as practitioners, not knowing what you're dealing with. And it ends up with, often you see people building systems where when you've read a bit about the problem, you're like, why did you do this? This was such a bad idea. And that kind of propagates some errors. So I want to talk about how we measure error. So we tend to do it in terms of accuracy, precision, recall, and F1 measure. So I'm just going to go through these individually. Accuracy looks at how often our prediction is correct out of all predictions. This seems like a reasonable measure until you realize, as Helen mentioned, that there isn't a lot of hate speech compared to speech in general. So let's say that 95 out of 100 documents that we have are not hate speech. So 5% of our documents are hate speech, and our model learns, well, you know what, I'm just going to predict that none of it is hate speech. That means that our model will get 95% accuracy, which is a number that looks great, but really, really tells us that we need to look at why our model is getting that higher score and what that means. Precision tries to look at when we say that something is hate speech, how often is it then actually hate speech? So that's a lot more robust to it, to model to data imbalances. And then we have recall. So recall is best explained in terms of retrieval. If I ask of a system or of a person to find all books that are written by Brits, and it retrieves all books ever written, then my recall is 100%, because recall only cares about when you're right. It doesn't care about when you're wrong. And finally, we have F1 measure, which tries to harmonize precision and recall, because precision says, well, what we really care about is being right, while recall cares about we don't care so much about being right as long as we don't care about being wrong as long as we're right. And each of these different measures of error will guide your model towards a specific solution, and it'll guide your development towards a specific form. And that is what I have, because machine learning is not the end all, and we rely on error.